Hey Ryan, how are you?
Good, how are you?
Good. Um, all right. Are we picking up where we left off last time, or did you have something new you wanted to go over?
I think just pick up where we left off, because the things that I sent you is everything that's going to be on the quiz, I think.
Okay, no problem. And
I think it's,
sorry, go ahead.
I think it's just the area stuff, and then the disk method, washer method, and cylindrical shells.
Ooh, wait. So you have to do all three because we didn't cover all three last time.
Yeah, I have to do all three, and it's a calculator. So I don't have to, like, actually, I don't have to, I mean, once you get the integral, I should be able to, like, know how to do that,
Yeah.
um, but yeah, I don't need to know how to do anything past the integral, I think.
Okay.
Just use the calculator.
Okay, got it. Like, cause yeah, like that's he's preparing you for the AP obviously, cause there are a number of questions on the AP on the calculator section where they go set up but do not evaluate the following integral, blah blah blah. But in your case, it looks like you might have to also, in addition to setting up, like just plug it into your calculator, which is easy work. Now, so I had asked you, I left you. I did one question with the one about the sign um, on y equals sine x on the one page where we're working, and there were two additional questions that I left you to try on your own. I didn't. I mean, I kind of like very briefly talked about the washer method. We talked about the disk method, and the washer method is basically like when you revolve an area that will create a hole into your shape. Like by the way, are you in your room?
Yeah.
Okay, just making sure we're on the same page. All right. So so here. So like like it could be like entirely hollow in the middle, right? Like for the washer method, or it may be like um what is it? A cone removed from the solid, right? Like so, like if I revolved this region, obviously it would form some kind of a bowl if I revolved it about the x-axis. Whereas, like if say I revolve this region, and that's supposed to be a straight line. I revolve this strip, then it would be the same bowl with a cone removed, scooped out of it. Makes sense, right?
Yeah.
Yeah, okay. So, like, obviously, like, there's a little more to say about the washer method than just that, but that's like the big overview. Now, cylindrical shells, I'll talk about because I didn't talk to you about them at all. And it looks like we have a little bit of work, but I imagine you also did this a little bit in class, right?
Yeah, I think the launcher method seems pretty straightforward,
Yeah,
kind of like the other one, like that one equation that kind of fixes everything.
exactly. Um, Yeah, exactly. So, and I'll make sense of the cylindrical shells method. It's pretty cool, actually. If I had to pick a favorite, yeah, only a true nerd would say this. But if I have to pick a favorite, cylindrical shells is probably my favorite of the three, and you'll see why. So, but hold on. So sorry. Sticking to the script though, um, like we only have like half a page and one more. So how did you do with the two questions that the problem two and three that I left you with?
Um, I know he goes pretty easy.
Okay, so fine. Just a quick, very quick summary of what we had done. Recap is it is pi integral a to b r squared dx or pi integral a to b r squared dy for disk method. So this is disk. Now, um, let me number them one and two. How would you know to use one versus two?
Um, if it asks you to like rotate around the y-axis or x-axis,
Exactly. And say a little bit more. So what's the nature of R in one versus in two? Sorry, I'm intentionally asking a vague question. What is R like in 1 versus 2?
Alright.
Sorry, maybe that's too open
Oh,
ended. No, go ahead.
they're like it's like the same as like the equation when they give you the equation and it's like in terms of x versus in terms of
Exactly,
y.
exactly. Way to read my mind. Yes. And one, you go y equals junk that has to do with x, and two, it's x equals junk that has to do with y. The end. Okay. Um, Obviously we said like if it's x equals, then it's like the x and y axes have swapped roles. Blah blah blah. We talked about how you graph them, and the only other thing is like going back like even before the disk method, right? We talked about area and in air, like obviously, even for disk and washer and shell, you have to figure out what A and B are, but they're more straightforward, and you don't have to do as much work as like the area between two curves. So the very first item we talked about is area between two curves. Just a quick recap: what you have to do is like figure out which function is on top, which function is in the bottom. Otherwise, you need to set them equal so you find their points of intersection. And then if the top is f and the bottom is g, it's integral from a to b. First point of intersection is a, second point of intersection is b, and then f minus g and dx, and it may be like sideways, blah, blah, blah. Just a quick tip, right? Like if you have a and b, right, which are the 2 points of intersection, let's say a is here and let's say b is here, then, if you have a convoluted set of functions, right, the two functions are like weird, and you need to know which one is on top, and you can't graph them. One thing you could do to quickly cheat and check, is you could just take an x value between a and b and plug it into both functions, right? Let's say this x right here, and well, whichever gives you the higher value, that's on top. So that's a way to figure out like which is on top. Again, if like graphing it is like a more involved way of getting there. Okay. Now, like the disk method. Since you said that like the two questions are that I let. Well, that's for washer. Sorry, that's for disk. My bad. Let me slow down. So yeah, the two questions you did are for disk, and so you felt like they were easy. So like we don't need to go back to disk at all. For washer, the only thing I'll say is this, right? So it's very much like the disk method, as you said. The only thing is that like the formula becomes now pi integral from a to b of big R squared minus little r squared. And then it's either dx or dy depending on, again, if it's a function of y or a function of x, the function given, right? So pi a to b big R squared minus little r squared, sorry, and then it's dy, right? Now there are some subtle things. Obviously, like what I would do, right? Like, well, so has he represented anything like this? It's about the y and x. Hold on, let me look, because I might be like, I don't, I'm sure he will give you more involved questions, like like higher order versions of these, but like that's if you're rotating about something other than the x-axis and the y-axis. Oh yeah, okay. So he gives one, and for y equals 4. Okay, yeah. So exactly. So this is. I just want to make sure I don't tell you more than you need for your quiz. Okay, so that's what I was doing just now. Okay, so look. So obviously, like if you rotate about the x-axis and the y-axis in the visual that I have, and what you've got is this area that you're revolving, say, about the x-axis, then like this is little r and this is big R. And so the little r is the bottom function, the line, and big R is the top function, and you go from there, right? Now, looks like what I drew for big R is like root x. For little r could be y equals x, and so if I had to very quickly do it, root x and y equals x meet at 0 and 1, right? Yeah, so it would be like pi 0 to 1, and then big R we said is root x, so root x squared. Don't forget to square, and then minus the bottom r is x squared, and then dx, and it's over, right? Like, so this is a very basic example. So what if it's like more sophisticated than this, right? Okay, so most important of everything you need to keep in mind is draw your big R and little r from the axis of rotation. That seems pretty obvious. But yeah, do it. Draw them from the axis of rotation, and if you do that, then the first uh, function you encounter, that's little r, and the second function you encounter, drawing from your axis of rotation, that's big R. So like sticking to this script, right? Like I could have done, sorry, it was root x squared and then x squared dx, right? I could have rotated this same region about the y, and I get a different shape if I rotate it about the y, obviously, right? But you get a funnel, sort of, if you rotate it about the y instead of a bowl with a cone scooped out of it, right? And so if I was doing it about the y, again, I would stick to the plan, which is draw little r and big R from the axis of rotation. So if I draw a horizontal line from the y-axis, which is my new axis of rotation, the first curve I encounter this time is root x, namely y equals root x, right? And so that's little r. And then if I draw, like, another line until I counter the second curve, this time I've got big R is equal to a y equals x, right? Okay, cool. So then obviously this time you're using formula 2 if I number them. And it has to be in terms of y, big R and little r. Okay, simple. We said little r is y equals root x. Little r is y equals root x. You can manipulate that so that you get x by itself. So that way you have x is equal to y squared, right? And so then that's little r, and y equals x, big R, fine. That's x equals y, not much work, right? So this time, if we're rotating about the y-axis, as I said, the shape you'd get is like a funnel. It would look something like this, right? Okay, sorry. So if we execute it, it would be like pi, and the limits of integration, it just so happens that for these two functions, is trivial. They meet at 0 and 0 and 1, 1. So both x and y are the same, whether you're looking at it from a horizontal axis of rotation or a vertical one for the region. But so that makes it, but, be careful in your specific case. But you go, from 0 to 1, still 0 to 1, but along y this time. And what we said is little r is y equals root x, which we have to translate as x equals y squared. Big R is just y equals x, so y squared, because x is y, and then minus y squared squared, because that's little r, and then dy. Okay, cool. So I'll do the same example as a jumping point, and we'll like obviously dive into the problems that you want to look at, but I'll do the same one, but sorry, hold on. But this time, let's rotate, say, about y equals 2. So again, this point here is 1, 1. We know because I'm claiming it's root x and y equals x. Okay. So if we rotate about this horizontal line, y equals 2, then first we draw this line. Again, I'm sticking to my own advice, which is draw from the axis of rotation until you encounter, towards your region, obviously, until you encounter the first curve. That's little r, okay? And then big R would be this. I'm sorry, like it's not very interactive in these parts, but feel free to interrupt me at any point. Okay, so that's big R and that's little r. Fine. Well, actually, like here you have an opportunity to chime in here. So I've drawn you the lines that's somewhat helpful for what big R and little r should be, but go from there and tell me what little r is and what big R is.
Well, didn't you just say that little r, the line y equals rather, and below is y equals x?
Yeah, but like we're no longer measuring from the x-axis, and so what does if I hold on, let's go right here. Let's say that this is root x. Now, what does root x actually represent? Root x represents the height for a particular x. In other words, if you have some x here, root x would be the y value, which is this height. So that's not little r. That's not big R. Or like even in the case of little r, root x doesn't represent This portion that I drew, little r is right here. That's not root x.
No, so little r would be x equals y squared.
Close. Well, that would be if I was measuring it from the y-axis, and that's just me you translating y equals root x in terms of x. But yeah, like that would be like this way. Think about what we just did. So
It has to be in terms like from two.
yeah, like yeah, look. So again, it's annoying that I don't have a different color. Hold on, I'll try to do it using the highlighter. This yellow line, what does that represent?
From x.
Yeah, for this x, that's root x. That's the height. But then the distance from here all the way down here is how much?
From the yellow line.
From the axis of rotation from here all the way down.
Is two.
Exactly, it's a fixed value of 2. So then little r is the difference between that value and root x for any x. For this x,
Two by
exactly, that's root x right there. And then the whole thing is 2, so 2 minus root x. Make sense? Okay. And what's big R? There you go. Beautiful. Okay. So this is kind of like a slightly more advanced example, but you know, obviously, like it's pretty straightforward from here, which is you know like well, which we're not rotating about the x-axis, but we're still rotating about a horizontal line, a line parallel to the x-axis, and so it's still going to be dx. So long as you're rotating about a line parallel to the x-axis, you're gonna have to write dx. Make sense? Okay, so then you go pi. You've got your little r and big R figured out. The region is still going from 0 to 1. And so big R is 2 minus x squared. And then little r is 2 minus root x squared. And throw on your dx, and that's that. Fair? Okay, cool. Now, I'm going to... He hasn't asked you to do something like this in the worksheet that you sent me anyway, but because I'm slightly a paranoid person, just to cover your bases extra, I'm going to do the same region, but from a vertical line away from the y-axis. So we're still dealing with the same two functions. So let's say root x, and then x again, but you're rotating it about a vertical line like this, let's say. So, my bad. So, and this is actually a really nice segue to the method of cylindrical shells. Jesus Christ, sorry. Let's say, well, if this is -2, right? Then the vertical line I just drew is x equals -2. So, this time I want you to rotate it about x equals -2. And the only reason I'm doing this, Ryan, given that, like, you know, he doesn't have one like this on the worksheets that you've sent me, the only reason I'm doing it is to reinforce exactly what we had just done, and for you to also like understand, you know, the difference between a horizontal line versus a vertical line. So talk to me. What would you do here? And I'll look at what you just texted me while you do that. So figure out what you do. Go ahead.
what exactly do the nerve sheet for cylindrical shells?
Say that again.
The nerve sheet for cylindrical shells.
Oh, I see. Okay, no worries. Thank you. Go ahead.
So because it's somewhat like negative x equals two is like parallel to the y-axis,
Uh-huh.
we have to put it in terms of y first.
Okay. That's a good point. That's a start. Uh-huh.
And then,
So,
for example,
go ahead.
that would be y x equals y squared
Yep.
and x equals y.
Yeah, exactly. Y equals x, x equals y, same thing. Okay, go ahead. And so, how would you start figuring out little r and big R?
So you draw the line towards like the region.
Exactly. This time you're drawing. Obviously, we're drawing a horizontal line this time. That's little r.
The little r is going to be y equals red x, and it's going to be 2 minus, no, 2 plus y.
Yes, exactly. Even though it's a negative two, it's a distance. So first you have to cover the distance, the gap between the vertical line x equals negative two and the y-axis. That's the distance, a fixed distance of two. And then you got to go x amount horizontally until you encounter y equals root x. But y equals root x, x amount is y squared. Does that make sense?
Yeah.
So what is little r?
Um, little r is y squared plus 2.
Yes, 2 plus y squared. Very well done. Good. And the other one should be easier because it's an easier function. And so obviously, again, you draw a line until you encounter until you encounter the second function of your region. So that's little r. I drew it elsewhere, but whatever, same thing. Okay, go from here and tell me.
Big R is y plus 2.
Exactly. Big R is y plus 2. Exactly. 2 plus y plus 2. Same thing. And again, the limits of integration I don't like because they make this whole thing seem trivial. So it's pi integral from, from 0 to 1, because even along the y, the region is covered in those y values, 0 to 1. And otherwise, big R, which is 2 plus y, don't forget to square minus little r, 2 plus y squared, and then dy. Fair? Okay, cool. Nice. So, now, sorry, we do, what do we do? Oh, yeah, so, I don't know why I'm got, like, um, okay, I'll share. I think it's okay. Like, I was, first, I don't even know how it entered my mind, but I was thinking about a girl, like, for, like, like, the 2 seconds where I had a brain fart. Um, so forgive me. I think no. Sorry. Okay. So like you said, 2 and 3, those things are easy, so we don't need to go. Oh yeah. Okay. I know what to do. I know what to do. But like, and this is why I was saying that this is a nice segue to like cylindrical shells, because you can do cylindrical shells when you're rotating about a horizontal line, which is like parallel to the x-axis, but it's like really really atypical, and I don't think as uh, as interesting as Mr. Clark likes to make questions, I don't think he's gonna give you um, one where you rotate about sorry, yeah, around the y-axis. Yeah, he's not going to give you a cylindrical shells question where you rotate about a horizontal line. So I just want to make sure, sorry, because I like the last minute I was like a little all over the place. Well, can you summarize what I just said about cylindrical shells? The hint I gave you.
It's never rotating around the x-axis.
Yeah, or anything parallel to the x-axis. It's pretty much every time you rotate about a vertical line. Now, just to, on a note of like mathematical precision, it's possible to do it over a horizontal axis, including the x-axis or something more interesting. But it is very unlikely he'll give you one, and it won't. It's not going to be on the AP one like that anyway. So cylindrical shells basically like be like, all right, my hint is like if it's rotating about a vertical axis. Make sense?
Yeah.
Okay, so we had just done a vertical axis, but use it for washer, a more interesting version of washer. So I'm gonna do the same question, same exact everything, but using cylindrical shells. And then I'll offer you a second example to show you why we need cylindrical shells. Because you must be asking, like, hey, wait, like, if you have done this problem using washer, why would we need cylindrical shells? Why don't we just use washer all the time? Well, in my next example, I'll explain why cylindrical shells are necessary and You can't. Anything you could do with washer about a vertical line, you can do using cylindrical shells, but not the other way around. Everything you can do with cylindrical shells, you can't necessarily do with washer. And my next example will like clear that up. Okay, so how do we do cylindrical shells? So the idea, but of cylindrical shells is like this. So imagine you have a roll of paper towel, and on your roll of paper towel, you like pull up some of the papers and pull down some of them to form a solid. Like so, basically the idea is that like you're able to form. Sorry, the drawing is not gonna work out well. You're able to form your solid by taking layers of paper towels whose heights will change, and it's not hollow in the middle, it may be hollow in the middle. So fine. So for cylindrical shells, this is always kind of like how for washer and shell, we start by drawing our radius from the axis of rotation. This is a must first step for cylindrical shells, or I think the most helpful first step. Draw a height in your region. Always do that. Then draw a radius from your axis of rotation to that height. So again, first thing you should do is draw a height in your region. Then draw the radius. Fine, and this is why it's called cylindrical shells method and why the paper towel makes sense. Because if I rotate just this little strip of height that I drew in my region, what it would form is a cylinder. Sorry. I hope I get it right. It would form a cylinder whose radius is as displayed, and whose height is just that little bit. So it's not a very tall cylinder, the one I just drew. You get it? Yeah, and if I drew another cylinder next to it and another one by rotating different heights, then you can see the paper towel analogy and how the solid is being formed. There are pictures. Like, hold on. Actually, do it away from me, like so, or I'll do it right now. My bad. Sorry, I don't want to take session time, but hold on. It might be worth it. Cylindrical shells. And if ever, we work on like, sorry, we go 5 minutes over the 60 minutes. 5 minutes is on me. But anyway, I just want to make sure. Sorry. I find the right picture for you. Well, whatever. You could have Googled it yourself, but I'll do this. This one is pretty good. So, because it's worth the time I'm taking to do it. Sorry. It's better than any drawing I can send. I can make my own. So check out the text I just sent to you. Yeah, exactly. So it's like layers of paper towel that form your solid, right? So okay, good. I'm glad you appreciated it. That reaction is just about right. Thank you. Okay, so now, so like obviously since they're cylinders, right? We need the surface area of a cylinder, right? And what's called the lateral area, because like, well, we obviously don't need the top and the bottom. We just need like a layer, a layer of area of a cylinder. That's what we need to figure out. Okay, fine. So, well, if you cut up a cylinder with a scissor and lay it down, it's a rectangle. It's a rectangle whose width is the circumference, 2 pi r, and its height is h. You follow?
Yeah.
Exactly. So that's the layer of the cylinder. So and that's why it's important to draw r and to draw h. Obviously, if this function is f and this function is g, right? And since we're rotating about a vertical line, right? Um, well, sorry. Although we are rotating about a vertical line, remember, um, for washer, when it's a vertical line, you have to do dy, and when it's a horizontal line, you have to do dx. So cylindrical shells is an exception. Uh, Even though it's a vertical line, it's dx because the cylinders are growing horizontally. Like the increment from one layer of the paper towel to the next, it's going along x. So there are changes in x. That's why it's dx. But anyway, um, we have one layer of a cylinder, which is 2 pi r h. And then we want to add, and I've told you this before, add in math terms means integrate. Uh, uh, that's lowercase sigma. And then throw your dx. And that's it. This is the formula for the cylindrical shells method. 2 pi r h dx. Now, I of course like it's simple. Like I sorry, I was gonna say I made it. If I'm making it seem trivial, it's well. You've now that you've seen where it all comes from, it's pretty simple. It's not hard. So I don't. I also don't want to make it seem like it's a sophisticated idea. It's not. So first, just memorize that formula, right? Obviously, the 2 pi we can pull out, and then obviously the a and the b are still bounds of your region. So in this specific example, they would be like 0 and 1 once again, and then r and h dx. Now, the reason why I was so like adamant on you drawing h is because well, it makes it very clear what h is if you draw it in your region. What is h based on my drawing in the region?
Um, and then
Yeah, you do. I'll draw you a H somewhere else. Here.
oh, which is the distance between the two lines.
The distance between the two functions. So I've named them. So use the names given and tell me.
Which is the distance between little r and big r.
It's the difference between the two functions. There is no little r and big R. In cylindrical shells method, there's only one r, and it's the radius
No,
r you draw to your generic height. I drew a generic height in my region, right? A random height, and I drew r to it. So the r is just that, the horizontal distance. But h is that little vertical line. I'll put in highlight. Go ahead.
between f and g.
Yeah, exactly. H is f minus g, and they're both going to be in terms of x because I have a dx right there. Make sense?
Yeah.
What's r? There's only one r. What's r?
The radius.
Yeah, and so tell me what is r?
Distance from, well, in this case, x equals -2 to the function.
Well, Look at where r encounters our region. Does it encounter it at either function?
It captures at h.
Yeah, at the generic h that I drew. But that generic h I drew corresponds to some random x down here, right?
Yeah.
So this distance is some x. This distance is some 2. So what is r, little r? Or what is r, period, sorry.
X plus 2.
Exactly. And I can make that simpler, Ryan. Um, um, if obviously if it's a simpler question, you're rotating about the y-axis for cylindrical shells, right? Then r is always x if you're rotating about the y-axis, because then it would be just this distance, and that's just a horizontal amount of x. Make sense?
Yeah.
Yeah. But if you're rotating around some line that's to the left of the y-axis, then you have to first cover that gap, so that positive distance. It will always be that plus x. And if on a weirder question, which I don't imagine you'll encounter, if your region is over here, right? And you have your axis right here at x equals 1, then you draw your generic height. R is this time this bit, and that is x, which is all that, minus 1. 1 being that distance right there. But it's unlikely he'll give you a situation like this. Make sense?
Yeah.
Okay. But otherwise, as I said, like for cylindrical shells, first of all, formula is 2 pi integral RH dx, always. And then A and B. And second of all, if you're rotating about the y-axis, R is always x about the y-axis, and H is just the difference between the top function and the bottom function. And if again, otherwise, if the vertical line you're rotating is not the y-axis and it's like some x equals a negative number, it will be the positive version of that number plus x for R, always. Okay. Oh yeah. Like real quick, let me explain why we need the method of cylindrical shells. So, like, say you have this parabola. If this is x equals 3, then the parabola is defined by x times x. What is it? So x minus 3. Yeah. Right. Yeah. Okay. So this would be like, so that's y equals x squared minus 3x. Right. That would be my parabola. Now remember, earlier in the previous question, right? Like I did this using shell and I did it using washer. Because in washer, right, you have a little r and a big R. Little r being the first function you encounter, big R being the second function you encounter. But check this out. If we come back to this situation, my current situation, well, it doesn't make sense to use washer, because if I draw a little r, it would be right there, and then big R, it would be right there, but that's the same function. I can't subtract the function from itself. I would get 0. So this is why we need cylindrical shells. Because, well, if the function is the same function, and your region that's bounded, then big R and little r are not two different functions. It's the same function. It doesn't make sense. I'm sorry, I just repeated myself, but it's intentional. But, the cylindrical shells will do it. Why? Because I draw my generic height right there. I gotta ask, like, the people who, like, fix the site, like, about the color coding, because I think it would have been useful. Sorry. But for now, I'll use a highlighter. So, because now, look, check this out. If I draw that's R, and there's only one R, so there's no worries. And let's say that this is x equals negative 5. Obviously, R is equal to what? This distance is x. This distance is positive. Yes. Always, whatever number is, take it an absolute value plus x if it's not the y-axis for cylindrical shells. Make sense? Okay, so 5 plus x. And h is just the function. There's only one function this time. So it's not a top minus a bottom function, because I'm talking about this whole region. And that's just the parabola. So h is x squared minus 3x. So then you just be like 2 pi, and my region goes from 0 to 3. So 0 to 3, r is 5 plus x, and then x squared minus 3x, and dx, and you go from there. Make sense? Okay, cool. All right, so I've done all the overviewing that I would have liked to do, and provided my own examples, and so there isn't much to do from your worksheets, but we could do the problems that you want to do from your worksheets. I suppose we can start with the most recent one you sent me, or we can go back to the washer ones. So whichever you want to do in whatever order. Okay, got it. So go ahead and read it for both of us.
Um, find the volume of the solid generated from the region bounded by y equals e to the x, the y-axis, and the line y equals 4 is revolved around the y-axis.
Okay, got it. So, sorry. I mean, I imagine that you know how to graph all of these, and since you have a calculator or you're allowed a calculator, you don't, you couldn't possibly have trouble with it. So I'll just draw the region y equals e to the x, um, the y-axis of y equals 4. So let's say y equals 4 is here, and the y-axis. So that's this region right here. Okay, got it. And it's revolved about the y-axis. So this is super trivial. This is very easy. Wait, could we have done washer? Yeah, we could have just done this with washer, because like there's
Yeah,
no.
I think
Go ahead.
the washer and the sheet needed the same equations.
Got it. Yeah, we could have done washer. But since he said to do cylindrical shells, talk to me. What's the first thing I should write down? Well, I'll just say it so I'm not making you guess what's on my mind. First thing you should write down, you should be like, duh, is the formula 2 pi and then RH dx. Go ahead. Talk to me.
Um, so
Well, you need to figure out R and you need to figure out H.
yeah, the line.
The next thing you should do, bud, draw a generic height. So let's stick to the script 100%. Draw, write down the formula, step 1. Step 2, draw a generic height. Step 3, draw R from the axis of rotation to the generic height.
So the generic height is 4 minus e to the x.
Yes, very good. 4 minus e to the x. Yes, beautiful. Like, this is why I love working with you. Because, like, I don't need to repeat anything, like, more than once. That's great. Okay, now, uh, like, remember, very quick, because this is on my mind. We're not digressing too much, don't worry. Like, when we did this problem, like, several times, right? Like, obviously, if you rotate about the x-axis versus rotate about the y-axis, the volume you get is different because they're not the same solid. One of them, as I said, is a funnel. The other, when you're rotating about the x, it's a bowl with a cone scooped out of it. But we said that in this problem, you could have done it using cylindrical shells or the disk method, this question that we're on. And if you do it either way, you should get the same volume because it would be the same, this time, it would be the same solid either way. Make sense? Okay, all right, but let's finish the task at hand. So we're basically done. You figured out H, which is the hardest part. And then what's R?
Um,
D-
or
Go ahead.
it's just x.
Yes, you shouldn't even think. If you're rotating about the y-axis for shell, we said R is X, period. The end. So replace this R with X, replace that H with 4 minus e to the X, and it's done. Oh yeah, I suppose we have one more thing, which is limits of integration.
Is the limits of integration thing like where you find where you're integrating from?
Say that again.
Limits of integration meaning look to find where you're integrating from.
Yeah, from what number to what number?
Yeah. Would it just be sort of
That part, yeah. Go ahead.
Here it is. U of
Let's see. I don't know. Like, so we need to know where
four e to the x.
we need to know where e to the x is equal to 4.
Yeah.
And so the way we do that, I'm sure you know how to do this, is take the log of both sides. Ln of e to the x is just x, so ln of 4. So the other limit of integration is the natural log of 4.
So if I'm on the test and I'm doing it, like it just doesn't give me a graph, should I be graphing it every time?
Yeah, as you can see, like a lot of this stuff is made simple if you have an idea of what the region looks like. Like drawing the generic height and drawing the radius are like crucial to these cylindrical shell methods more than any other, like and the washer too. So yeah, it's very valuable to have an idea of what your region looks like. Okay. And next, the next problem, I suppose.
Find the volume of the solid generated when the region bounded by y equals negative x squared plus 8x minus 7. The line y equals x minus 1 is revolved around the line x equals negative 1.
Okay, is revolved about the line x equals negative 1. Got it. So, uh, like again, we should start with a visual, and like I mean, I suppose I could factor, but so if I minus, and you obviously have a calculator, so you could do this on the calculator, but I think it's quicker this time if we just factor. So like this, and then so that's minus, and then what is it? X minus 7, x minus 1. That'll do the job. Yep. Okay, so x equals 1 and x equals 7 are the two intercepts. Fine. So my bad. Um, x equals 1, x equals 7. Let's say here and here. I don't really need to know how high does it go. Well, okay, so we can average them, right? So 1 plus 7 is 8 divided by 2 is 4. So we know that the maximum will occur at x equals 4. And it's a parabola facing down. Good. So if we plug in 4, we get what? Minus 16 plus 8 times 4 is 32, right? Minus 7. Can you help me with the arithmetic? What's that? I'm not very good at arithmetic, and I'm not just being like funny. 9?
Yeah.
Yeah, I should never beat you at arithmetic, right? Sorry. So 9 is like right here. I am serious. I'm like very poor. Okay. So there and there. Okay. Got it. So that's what that looks like. Y equals x minus 1 is like, well, it's a line. It looks like this. Good. So our region is like, and we definitely have a portion below the x-axis. That should be very clear. And so my visual is very accurate. Accurate, we can say. Okay, fine. So again, this part you could have done with your calculator. I'm not going to shade because we need to draw stuff in it. Oh, come on, come on. Okay, good. All right. So and it's rotated about what again?
So line x equals negative 1, I think.
Yes, exactly. I saw. I was asking a rhetorical question to make sure that you know. Yeah. Anyway. So x equals negative 1. I don't think the parabola. I don't think this meeting point catches it, but we can find out. Like, how would I figure out? We need to do that anyway. We need to figure out the places where they intersect. So, uh, yeah. How would I figure out what this point and this point are?
Set the equations equal to each other.
Exactly. So I'll do that real quick. Minus x squared plus 8x minus 7. Jesus. Yeah, my bad. Equals x minus 1. So then if we subtract 1 from both sides and add 1, that's going to say minus x squared plus 7x. And then minus 6. Very well constructed question, Mr. Clark. Because this 2 factors, and it's going to be like x minus 6 times x minus 1, right? Wait, what? No.
No.
Yeah.
Uh,
Oh, no, yes, yes, sorry. Because we were to factor out a negative 1. Yeah, my bad. And then that's minus and that's plus, so it works out. Okay. So equals 0, sorry. So x equals 1, x equals 6. So they needed x equals 1. What? Really? Yes, yes. So my visual is not accurate. Um, yeah, okay. Ignore my line. My line was not accurate. So there isn't a portion below the x-axis. The line looks like this. It starts at negative 1 and it cuts through like that. So the region is entirely above the x-axis. So I take that back. My bad. Okay. Anyway, this the reason why we had to labor so hard for this, right? Is because well, we need to draw our axis of rotation accurately, and so and that's x equals negative 1, the line I just drew, and that's very important to everything we're doing. Okay, got it. And is revolved about, and this is this is cylindrical shells, right?
yeah.
Yeah. Yeah, so remember the one that I said is like too interesting and is not gonna be on there. Apparently it is because it's Mr. Clark. Um, all right. So okay, so he did put that on, but not a big deal. So basically, like there's an exception to everything I told you earlier, which is um. Wait, what? Sorry. Are you sure this is cylindrical shells?
Uh, yeah, it says this is the zone where it says find the volume of stuff the solid generated by the region bounded by y equals negative x squared plus 2x minus 7 divided by y equals x minus 1 is revolved around the line x equals negative 1.
Yeah, but I'm saying though like that we could um
You could use the washer method, right?
yeah, that's what I'm saying. I'm saying, and actually, this question would be impossible to do using cylindrical shells because let me explain. Like, well, first of all, we'd have to change a few things if you were to do this. This is the one that I said would be an exception. I said cylindrical shells is always when you rotate about a vertical line. We're not rotating about a vertical line here, and so this would be like that very rare uh, exception that I mentioned. But like I said cylindrical shells when it's a vertical line is always dx. So for starters, if we were to do cylindrical shells here, we'd have to write dy. That's not a problem. The only problem is our region is not uniform. Like, because like in these parts, right? Like, let me draw this line. Like in this part, it's the line minus the parabola for the height because well you that's where you draw the generic height, like somewhere there or somewhere over here or somewhere over here, our generic height, right? And so in the bottom area in this part, sorry, hold on, in this part it would be the line minus the parabola, and it would be like a function of y. They'd have to both be turned into to be about y. That makes it very difficult because one of them is a parabola. You can do it, but it's very hard to make a parabola in terms of x turned into be in terms of y. You'd have to use a quadratic formula. The other problem is in this region, you get it. You can't do this using cylindrical shells, is all I'm saying. And that other part, you'd be subtracting the function from itself, and so that won't work.
I mean, I just send you what he did. I just like don't understand it.
Okay. We could do washer here, and that's what we're gonna do because you can't do cylindrical shells here. Whatever he did, if he did cylindrical shells, it'd be wrong. What did he do? Oh, I'm a dumbass. Sorry. He said about x equals 1. I drew a line at y equals at x equals negative 1. Well, okay, fine. I mean, did you get what I was saying though?
Yeah.
Okay. So you couldn't do it again. Just to reiterate, you couldn't do it about the line y equals -1, but he said x equals -1. So you can't do it because that's a vertical line. You should have corrected me, Ryan. Sorry, it's okay. It's not your fault.
Yeah, it was like -1, so I was like, oh, that seems right.
Yeah, no worries. X equals -1. That's funny. Okay, fine. So yeah, this is very doable. So fine. I mean, you know all the tools. So you talk. Like, how do I start?
So you write the equation.
Yep.
So 2 pi the integral RH.
Yep.
And plus you.
Thank you. Go ahead.
And then you determine your h. So that's going to be 1 plus x.
Hmm.
It'll be 1 plus x.
You're overthinking. Draw your generic height in your region. Draw your radius. So let's stick to our script 100%. So you told me the first step correct. Write down the formula. The second step, draw a generic height. I'll highlight it in yellow.
Um,
What's the generic height that I highlighted in yellow?
what's the peak at?
It doesn't matter what the peak is. It's the top function minus the bottom function.
Oh, yeah.
It's okay. So it's just the parabola minus the other line. So it's
It's negative x squared plus -7.
But
Minus,
you're super smart, and this stuff is easy. Don't overthink. I think that's what you did right there. You overthought.
yeah,
It's okay.
the minus.
Yeah, and obviously, like, I'm sorry, I don't need to say this. So sorry if I'm being annoying, but make sure that, like, whatever function you're subtracting, if it has more than 2 terms, put it in a parenthesis. Okay. So
And then r is 4.
R is what again?
1 plus x.
Yes, that's good. My bad. So I should have like been giving you credit there because I think that I just didn't know that if you were mentioning R or H. But yeah, very well done. R is x plus 1. So if I simplify the H, it's like minus x squared plus 8x minus 7, and then minus x plus 1, blah, blah, blah. Simplify that, and you get there, and you've got your R and you've got your H, so you don't need anything else. We know the limits. Actually, what are the limits?
Actually, from 1 to 7.
Yeah, 1 to what again?
7.
When we set them equal, the two functions, what did we find they were? 1 and... Sorry. Earlier, when we set the parabola equal to the line, we figured out that their point of intersection were 1 and what again? 1 and 7 were the x-intercepts of the parabola. The region ends at 6. Oh, good. Oh, good. So 1 and 6. But obviously, like, you know, you would have set the two functions equal to do that. So I trust that you're good there. Fair? Okay. So go ahead. Do you think we need to do another washer example? Because now that we've done these two, I like his visual. It's really cool. And the solution you shared. He's a great teacher. Like one of the best I've ever come across. But anyway, so sorry. So, do you think we need another washer example, or you feel confident there?
I feel confident there. I just don't like. I don't know how to tell if it's like a cylindrical shell washer or what's the other one called?
A disc?
Yeah, but I don't know how to tell if it's like
Sure. So very quick. Um, anything you could do with washer and shell, the first two, right? Anything you could do with the two, you can do using cylindrical shells. So cylindrical shells is like the patriarch, if you will. Now, otherwise, uh, washer versus disc is very obvious, right? Washer, you do washer if when you spin your region about the line, it has a hole in them. It's gonna create any hole in the middle. Um, and that's what a washer is, right? Like I don't know if you've been to Home Depot. It's like the little metallic things that look like that, hole in the middle, right? And that's why it's called the washer method. Uh, Disc is if there is no gap in the region and the axis of rotation. So if it's so the previous example, we said even though he had us do it using shell, we said we could have done this, and the reason that was correct is because look at the region. We're spinning it about the y. There's no gap between the region and the axis of rotation, and so you do you do disc there. But obviously, like we said, anything you could do with disc or washer, you can do using shell. So,
So I can use shell for everything.
yes, exactly. Way to summarize it. And so you could do that, but hopefully, like he hints you. If he doesn't hint, like obviously you understand the distinction between washer and disc. Um, and if we return to this, since you didn't have another question, the sorry, the thing I wanted to know is like if we could do this using washer, right? Like, and the answer I'll just give you the answer. Like I contemplated doing this one with washer. Remember we did it with cylindrical shells, but we can do washer, and the reason is like for washer, right? Like we would have to draw little r and big R. So here's to help you in answering the question you posed. That's little r. That's big R. There's an issue. What's that issue?
The same function.
Yes. And if I drew big R and little r somewhere else, look, that's little r and that's big R. So the region is not suited to doing um, the washer method because well there are places like the new ones I drew at the bottom where it would be two different functions, but there are places specifically above here where we'd have to subtract the function from itself, and that's not possible. So that's another clue one. Yeah, okay, I can't do washer here. I gotta do shell.
Alright.
But the most yeah, sorry for interrupting. The most important hint for shell is a vertical line. When you're talking about a vertical line and there's a gap between your region and the axis of rotation, you automatically have to be thinking it's either washer or shell, and then you can make the distinction based on what we just did. Am I having to subtract the function from itself? In that case, you're pigeonholed into shell. Okay, sorry.
The horizontal lines are only the disk method.
The disc and the washer method.
Okay.
Yeah, sorry. Just I know you're like a great listener and you got it all, but just to hammer that to death, like just to be clear that we did do a horizontal line and with washer. Here's that example. And this and while we're at it, this should also clarify like when you have to subtract to find r versus other situations like these ones where you have to add r.
Yeah.
Okay, cool. And as I said, I don't know when you would review. Like, what's really cool about the site now is, like, we're on page 18, so all our work from the previous days here, all this will be here if you need to come, like, tomorrow morning, like, log in and look at it, okay?
Yep.
Okay. You, again, like, you're such a lovely kid. It's like, it doesn't feel like work. So, thank you for making it so easy to teach you.
Thank you.
You're very welcome. Have a wonderful night, okay, bud?
Yeah. You
Okay.
too.
Text me if I have any questions. I'll be up for at least another couple of hours.
Alright.
Okay.
Thank you.
You're welcome. Bye.